Hi, welcome once again to Mathematics as a Second Language, where today we're going to look into division in a little bit more detail. In other words, when you say, for example, that in a certain classroom, the ratio of boys to girls is 3 to 2, it means that for every 3 boys, there are 2 girls. Doesn't sound like a fraction problem that way, but it's just another way of saying 3/5 of the students are boys and 2/5 are girls. In other words, 3 out of 5 are boys and 2 out of 5 are girls. So that's what we mean by a ratio, and we often treat them as fraction problems. So let's just take a look at a typical type of a problem and show how we traditionally handle this as a rate. And when I say traditionally, I haven't been in elementary school as a student for a very long time. And so what I call traditional may be something that's already been outmoded for a long time, but I'll just share to keep it non-controversial, I'll just share with you how I was taught to do the problems. It was called setting up a proportion. And the problem was, at a constant rate of 5 pounds for $6, how much will 7 pounds cost? And sometimes students will say, 7 pounds of what? Well, you put in whatever you want, but if the 5 pounds are $6, whatever the 5 pounds is modifying, so is the 7 pounds. And the other thing I want to stress is, at the pre-calculus level, we always assume rates are constant. When we say a man traveled 100 miles in 2 hours, we say what, the average speed is 50 miles per hour? But that doesn't mean he traveled at 50 miles an hour the whole trip. He might have been going 60 or 70, stopped for a little while, stopped in traffic, whatever it happened to be. In other words, if your average speed for a 2-hour trip was 50 miles per hour, all it tells us is that you went 100 miles. It doesn't tell us how you did it. So I just thought I would emphasize that, because sometimes I'll forget to use the word constant, and I just wanted to make that observation. Well, we were taught to do something like this. Write the 5 over the 6, and 5 is modifying pounds, so opposite whatever number we put in has to be modifying pounds. That means the 7 is modifying pounds. The 6 is modifying dollars, and we don't know what that is, so we'll call that a question mark. Then we were told to cross-multiply. 5 times question mark equals 6 times 7. So question mark was 7 times 6 over 5, which is the same as 42/5, which is the same as 8 2/5. And since 1/5 of a dollar is 20 cents, the answer would be $8.20. Now, of course, you could also, the teacher said, it doesn't matter. You could have started with 6 over 5, and since the 6 is modifying dollars, and you're looking to find the answer in dollars, opposite the 6 has to be the question mark. Then the 5 goes with the 6. It doesn't go over here. The 5 and the 6 go together, and the 7 goes with the question mark. If I had to memorize, I like this way better than this, because here I don't really have to cross-multiply. All I have to do is multiply both sides by 7. You see? And I get 42/5. And if it's easier to see by writing the 7 over 1, that's fine. Now, what I wanted to show you in terms of the adjective noun theme is what this really means. The 5 and the 6 here weren't just arbitrary numbers. The 5 was modifying pounds, and the 6 was modifying dollars. And then we said because the 5 is modifying pounds, the question mark has to be modifying pounds. Now, I want to show you in terms of the adjective noun theme why this was the case. 5 pounds for $6 is another way of saying 5/6 of a pound per dollar. And question mark over 7 says question mark over 7 pounds per dollar. The reason we could write that 5/6 equals question mark over 7 is that the two numbers, the two fractions, were modifying the same noun. The 5/6 is modifying pounds per dollar. question mark over 7 is pounds per dollar. And in fact, when you cross multiply here, just look at the nouns. This is pound dollars, and this is pound dollars. The nouns still line up. Now suppose by mistake, and by mistake I mean you didn't do what the teacher told you. See, this still is modifying pounds. This still is modifying dollars. But suppose you put the pounds down here. See, you didn't line it up correctly. You see why you can't compare the 5/6 with the 7 over question mark? The 5/6 is modifying pounds per dollar. The 7 over question mark is modifying dollars per pound. Since they're not modifying the same noun, we can't equate them. And again, notice what would happen if you did cross multiply here. This is how the nouns help you. Here you're multiplying pounds by pounds, so you get pounds. Here you're multiplying dollars by dollars, and so you get dollars. Okay? And how can these be equal? I mean, they're two. It's like comparing inches to apples. Pound is a different noun than dollar over dollar. So how can these be representing the same amount? That's the clue that you have if you understand the adjective noun theme. The way I happen to like to do it is what we call the unit pricing theme. For example, you can write this abstractly. If you know how many A's you get per B, and you multiply that by the number of B's, that will give you the number of A's. In other words, if you can get $6 per 5 pounds, I can multiply both sides here, divide both sides by 5, and I find out it's 6/5 of a dollar per 1 pound. Okay? $1.20 per pound. Once I know this, all I have to do is when somebody gives me the number of pounds, you see, I know how much it costs per pound. So if somebody says, how much does 7 pounds cost? I just multiply that by $1.20 and get $8.40. If there's how much does 10 pounds cost? $12. Okay? So 5 pounds for $6 is the same as saying 5/6 of a pound per dollar. And I just thought that's kind of a nice thing to know. And so let's again go to how we make all numbers whole. Here's another fraction problem. At a constant rate of 2/3 of a pound for $6, how much would it cost to buy 4 pounds of cheese? Well, let's do this the mechanical way. Per means divided by. So $6 per 2/3 of a pound is 6 divided by 2/3 dollars per pound. Okay? Now, I don't want to invert and multiply. I want to make this into a whole number problem. This is really a 1 understood over here. How can I make this into the quotient of 2 whole numbers? If I multiplied by 3, that would cancel out the 3 over here. So all I say is, if I bought 2/3 of a pound 3 times, I would have paid $6 3 times. So that would be $18 for 2 pounds. That's 18 divided by 2, dollars per pound. And there's the answer, $9 per pound, without even having to work with fractions. Now, if I was comfortable with fractions, I could say that 6 divided by 2/3 is 6 times 3/2. See, I'm invert and multiply. Multiplying across, that gives me 18 over 2, and 18 over 2 is 9. So again, you can use all these mechanical recipes. All I'm saying is, if you start the students off by having them being able to see what they're doing and why they're doing it, the mechanical recipe becomes very easy. They won't even be thinking about it after a while. On the other hand, if they memorize, they'll always be thinking about things. Is this where I invert and multiply? I've seen students multiply by inverting and multiplying. I mean, it's crazy what kind of things you can do if you're doing things just by sheer memory. Okay? Let's look at another problem that might look very complicated and see what we could do with that. I'm not going to do too many problems. I just want you to see how you can convert any fraction problem into a whole number problem. A car travels 2/5 of a mile in 3/7 of a minute. okay? And we want to find out how many miles per minute it went. See, so it went 2/5 of a mile in 3/7 of a minute. The 5 and the 7 leads you to believe you want to deal with 35. So you say, if I spent 3/7 of a minute 35 times, I would have gone 2/5 of a mile 35 times. So 5 goes into 35 7 times. 7 times 2 is 14. So you would have gone 14 miles. 7 goes into 35 5 times. 5 times 3 is 15. So you went 14 miles every 15 minutes. Now again, if you want to make this sound scarier, you went 14/15 of a mile in 1 minute. Can you see why? If you want to get rid of the fraction here, you would multiply by 15. And this would say what? You could also multiply the time by 15. So you would have gone 14 miles in 15 minutes. In other words, it sounds funny, but all you have to do, if you're intimidated by things like 14/15 miles per minute, just write it this way, 14/15 miles per minute. Then extend the division sign, and it becomes what? 14 miles per 15 minutes. And again, I only wanted to do enough problems this way to show you the power of the adjective noun theme. And you remember I said at the beginning of our course, probably the very first lesson, that my goal wasn't to make you give up how you teach a topic and have to learn my way. It was that I told you that after 40 years in the community college classroom, I found a way that helps students understand fractions better. And I just want to share that with you. And I may have mentioned this before, but look at it this way. If I have 6 tools and you have only 5, it's possible that your 5 are so powerful that they're better than my 6. But what if my 6 tools are your 5 plus 1 more? How can I be worse prepared? All I'm trying to show you is one more method that you can use if students don't seem to be getting it by the other methods that you're using. Oh, my subliminal hope is that you like my way so much, you'll pick that as choice number 1. But that's not the important thing. The important thing that we have to keep our eye on here is that our goal is to have the students not necessarily become better at math, but to stop being afraid of it. And with that in mind, I think I've said enough for this lesson. Let's go to our practice problem. It says, on a certain map, the scale is that 2/3 of an inch represents a distance of 50 miles. How many miles are represented by 4/5 of an inch on the map? Okay? Look at this problem, pause the video, work out the problem. When you're ready, resume watching the video, and I'll share my solution with you, okay? So going back to unit pricing, I would like the idea of knowing miles per inch, because once I knew the number of miles per inch, I could take that fractional part of the inch and convert that into miles. In other words, what we're told is that 50 miles in the real world, not on the map, are represented by 2/3 of an inch on the map. How could we convert this to a whole number? The denominator is 3. So let's take 2/3 3 times, see? And again, if it doesn't sound logical, the nice thing is you can always resort to the definition. How do you add fractions? You keep the common denominator, then you add the numerators. 2 plus 2 is 4 plus 2 is 6. 6 divided by 3 is 2. So that would work out. In other words, if I take 2/3 of an inch 3 times, I wind up with 2 inches. And if I take 50 miles 3 times, I wind up with 150 miles. So what now has the problem become? It's 150 miles per 2 inches. And now it's easy for me to do this because 150 divided by 2 is 75, and the noun is miles per inch. So now I know that every inch on the map represents 75 miles. So if somebody says to me, how much does 4/5 of an inch represent? The inch represents 4/5 of a mile. So the inch represents 75 miles, so 4/5 of an inch will be 4/5 of the 75 miles. 75 divided by 5 is 15, times 4 is 60, so the answer to the problem would be 60 miles. And again, if you did this mechanically, you might say 50 miles per 2/3 of an inch is how many miles per 4/5 of an inch. You can get the answer this way, but doesn't this seem a little bit more orderly? Later, the students on their own can say, why should I write all these words? I can just write these symbols in. In other words, there's nothing wrong with leaving out the words once the students recognize what the words really mean. And I think that concludes our lesson for today. I am going to look forward to seeing you all next time, when I believe the discussion will be to introduce mixed numbers. Until then, have fun, study hard.